Hello. In our video today, we're going to find a linear transformation which reflects any vector x, y, and r2, so any vector in the plane about the line y is equal to negative x. So you see my drawing here, y is equal to negative x. Essentially what we need to do to figure this out, we can do it a couple ways, but one of the easiest ways to do this thing is graphically. So I want to try to do things graphically in this case. What I need to do is pick out two vectors which would form a basis, but I also need to know what that transformation does to those two vectors. So I'm going to use these two vectors here. I'm going to use one in the direction of that line. So I'm going to use the vector 1, negative 1. Let's call that v. The reason I use this one is because I know what the transformation is going to do to that. It's just going to keep it there. Because if I'm reflecting it about the line and it's on the line, it'll just keep it there. Another vector I can use is something that would be normal to this line or perpendicular. And I will go ahead and use the vector 1, 1 for that. I'm going to call this n. So why do I use those two vectors? Because I know, first of all, what the transformation does to those. And second of all, they form a basis because we see that they're perpendicular. In fact, I could take any two non-parallel vectors in the plane, and that would give me a basis. Although I do need to know what the transformation does to them, and that's why I picked these two. Okay, so let's go ahead and use these vectors. So this is going to be my basis b. We're going to use some theory in a minute. So I'm going to call this vector, or this matrix P, is really essentially made up of the vector v and n, our basis vectors, in the columns. So I need to figure out, well, what does the transformation do to the vector 1, negative 1? Well, we know that that just keeps it there. So it takes it to 1, negative 1. It doesn't do anything to it. And what does the transformation do to that normal vector? Well, again, in this case, we know that it would take that normal vector and reflect it. So we get something like this. And that's just going to be negative 1, negative 1. So we know what that vector does. Okay, so now that I know what my transformation does to those two, I'm going to use some theory. So what I'm going to do is I'm going to try to find that standard matrix A, and if I can find the standard matrix A, then I will have my transformation. But one thing I do need to figure out is how I can write these two vectors here in terms of the basis. So I need to find this t of b. And so I'm going to do that over here. So essentially, how can I find this vector 1, negative 1 here with respect to this basis? So 1, negative 1 with respect to that basis. Well, when I look over here, it's essentially going to be one of these vectors and 0 of those. So if I find that b coordinate vector, it's going to be 1, 0. 1 of the first vectors and 0 of the second. So that's why I needed to pick ones that I know what the transformation did. Now I need to find this in terms of that normal vector. And that's going to give me negative 1, negative 1. But how does that go in terms of the vectors given? Well, it's really the opposite of this vector, right? So if I take 0 of these and negative 1 of those, I'm going to get this t with respect to b. So my t with respect to b is going to be these two columns. It's going to be 1, 0 and 0, negative 1. Okay, now I have everything I need to plug in here. So I'm going to use my calculator for help. Okay, so I have P stored in matrix A. I have this transformation with respect to B stored in matrix B, And then I took the inverse of P and I stored it in C. So now I'm going to go ahead and take that product. So I quit out of there, and I actually have A times B times B already typed in there. So when I go ahead and multiply those out, I get this matrix, and that is going to be the standard matrix that I need. So when I take P, which is 1, negative 1, 1, 1, times this matrix TB that I just found, that's where I had to use this basis, times the inverse, which was 0.5, negative 0.5, 0.5, or 0.5, sorry, I get this matrix here. So this is the matrix that I want. This is the matrix that will be our transformation A. So if I wrote that in terms of my transformation language, my transformation would really be my T of my vector x would be a negative x2 and a negative x1. Now let's see how this works on the vectors that we have. So if I take the purple vector, T of 1, negative 1, what happens? Well, I would take negative x2, which is 1, and negative x1, which is negative 1. It gives me that v back. That's good. And now if I take t of that normal vector, the vector 1, 1, I should get this negative 1, negative 1. And you can see that will be the case. So I take the opposite of x2, the opposite of x1, and I get my normal vector back. That's good. Let's go ahead and just try one more vector to see if our transformation works. I'm going to take the vector on the x-axis, so 1, 0. So let's sort of conjecture where that one should go. If I'm looking at this vector here, that should be on the x-axis 1, 0, where should it go if I reflected about this line? Well, I think you should say that it should go down here to 0, negative 1. Let's give it a try. So I get negative x2, my x2 is 0, so negative 0 is still 0, and now I have negative x1, and my x1 is 1, so I get 0, negative 1. Hey, that's just what we wanted. So this transformation will work. Well, I hope this has helped with finding a linear transformation which reflects a vector. You can also use it for rotations and all sorts of other things. You just have to find a basis that you know. And to be thorough, you should try this in R3 as well, and we'll do that later. Thank you.